For this week's video presentation, I will be discussing information pertaining to 4 different chemical buffer systems and how those systems work as defenses against pH changes within the human body. Hydrogen ion concentration is more easily expressed as pH, which technically refers to the logarithm of the reciprocal of the hydrogen ion concentration in gram moles per liter. In a neutral solution, the concentrations of both hydrogen and hydroxyl ions are equal. Neutral solutions have a pH of 7. When pH falls below a certain amount, 7.35 according to Sherwood, the solution is said to be acidic. When pH increases and goes above 7.45, the solution is then said to be more basic. To maintain a constant hydrogen ion concentration in the body fluids, there has to be an equal amount of input and output for hydrogen ions. Hydrogen ions, conveniently expressed as just H+, are added to body fluids through 3 different sources. Those sources are carbonic acid formation, inorganic acids, and organic acids. Hydrogen ions mainly come from metabolically produced carbon dioxide. Carbon dioxide chemically binds to water to slowly form carbonic acid. Carbonic acid then quickly dissociates to form hydrogen and bicarbonate as end products. Free hydrogen ions are also formed from acids. Most meat contain a large amount of sulfur and phosphorus. When those nutrient molecules are broken down, 2 of the strongest inorganic acids form as byproducts. Because sulfuric and phosphoric acids are strong, they both are able to largely dissociate to form free hydrogen ions into the body fluids. Aside from these inorganic acids, hydrogen ions can also be produced from organic acids as well. Like inorganic acids, organic acids partially dissociate to produce free hydrogen ions. What happens when pH levels change, and what are some of the defenses against those pH changes? Fluctuations in hydrogen ion concentration can have drastic effects on normal cell function. To name a few of the consequences, increased pH can lead to the depression of the central nervous system, whereas decreased pH can lead to the overexcitability of the nervous system, both the peripheral and central aspects. People can also die from extreme alkalosis or acidosis. To quickly compensate for situations in which the extracellular fluid becomes too alkaline or acidic, there are 3 lines of defense that help maintain hydrogen ion concentration. Those defenses include 1. Chemical buffer systems, 2. Respiratory mechanism of pH control, and 3. Renal mechanism of pH control. For our video presentation today, we will only be focusing on the first defense. Before we go into the specifics, let us talk about what a chemical buffer system is in general, especially how it works to minimize any changes in the pH. So what exactly is a chemical buffer system? According to Sherwood, a chemical buffer system is simply just a mixture in a solution of 2 chemical compounds. The mixture is important in minimizing pH changes, and it works when neither an acid nor a base is removed from or added to the solution. Buffer systems contain a pair of substances mainly those involved in reversible reactions. Reactions that are reversible make it possible for one of the substances to be able to produce free hydrogen ions as the concentration starts to fall, while another substance is able to bind to free hydrogen when concentration starts to rise. One of the most important buffer systems existing in the extracellular fluid that helps maintain constant hydrogen concentration levels is known as the carbonic acid bicarbonate buffer system. Carbonic acid and bicarbonate are considered a buffer pair because both substances are involved in a reversible reaction. Carbonic acid dissociates to yield free hydrogen and bicarbonate, while bicarbonate can chemically bind to hydrogen to form carbonic acid. To better understand the effects of this particular buffer pair, let us consider an example. Say, for instance, that there is an unbuffered solution. If a strong acid such as hydrochloric acid is added to this solution, all the dissociated hydrogen ions remain free in the solution. However, if the solution contains the carbonic acid bicarbonate buffer pair, an addition of hydrochloric acid can immediately prompt bicarbonate to bind to the free hydrogen to form carbonic acid. This weak acid slightly dissociates, causing a change in pH, which is way much smaller compared to the pH change that would occur if the buffer system was not present. The carbonic acid bicarbonate buffer system is important in controlling pH changes that do not necessarily result from fluctuations in carbon dioxide generated carbonic acid. This buffer system is effective in that both substances involved, the carbonic acid and bicarbonate, are abundant in the extracellular fluid and are both closely regulated. The abundance of each of the components of the buffer pair makes this particular system readily available to resist any pH changes. As for regulation, bicarbonate is regulated by the kidneys, whereas carbon dioxide is regulated by the respiratory system. The carbon dioxide generates carbonic acid. Aside from the carbonic acid bicarbonate buffer system, one other chemical buffer system that buffers the extracellular fluid, but mainly the intracellular fluid, is the protein buffer system. Almost all of the proteins can function as buffers in the human body. Hence, the protein buffer system accounts for about 2/3 of the buffering power of blood. As we all know, proteins are the building blocks of amino acids. Amino acids contain positively charged amino groups and negatively charged carboxyl groups. Having those charged regions contributes as to why proteins are such excellent buffers. The charged regions can bind both hydrogen and hydroxyl ions. According to Sherwood, the protein buffer system is extremely important in buffering changes observed in hydrogen concentration within the intracellular fluid because of the sheer abundance of intracellular proteins. The primary buffer against carbonic acid changes is the hemoglobin buffer system. Hydrogen ions generated from metabolically produced carbon dioxide are the main components involved in this buffer system. Carbon dioxide is normally diffused into the blood from the tissue cells where it is being produced at a continuous rate. As mentioned in one of the earlier slides, a great amount of carbon dioxide along with water forms a hydrogen ion and bicarbonate as end products within the red blood cells. This certain reaction is overall catalyzed by an enzyme known as carbonic anhydrase. At the tissue level, most of the hydrogen ions generated from carbon dioxide become bounded to a reduced form of hemoglobin, which then makes it impossible for the hydrogen ion to further contribute to the acidity of body fluids. In the absence of hemoglobin, the blood would become more acidic once it picks up carbon dioxide at the tissues. With an amazing buffering capacity, the hemoglobin buffer system is able to maintain pH levels, causing the venous blood to only be slightly more acidic than arterial blood despite the large volume of hydrogen ions. This reaction is reversed at the lungs, causing the exhalation of carbon dioxide from the body. Having to be the principal protein inside of red blood cells, hemoglobin accounts for about 1/3 of the mass of the cell. The last chemical buffer system that we will be discussing in today's video presentation is the phosphate buffer system. This buffer system is an important urinary buffer, but it also works as a buffer for the intracellular fluid. The phosphate buffer system contains two very different components: an acid phosphate salt that is able to donate a free hydrogen ion when the hydrogen concentration drops, and a basic phosphate salt that is able to accept a free hydrogen ion when hydrogen concentration rises. Similar to the carbonic acid bicarbonate buffer system, the phosphate buffer system contains two components that make up a buffer pair. Those two components are the acid and base that was mentioned just a few seconds ago. To make our discussion easier, I have included the reversible reaction involving the two components on this slide. The phosphate pair makes such a good buffer, however, the concentration of the components is very low in the extracellular fluid, so it is not very important as an extracellular fluid buffer. Phosphates are more abundant in the intracellular fluid like proteins, so this particular buffer system contributes significantly to intracellular buffering while competing with the intracellular proteins. The phosphate buffer system also works best as a urinary buffer. The way this works begins with an overconsumption of phosphates. When we consume phosphate amounts that surpasses the amount the body needs, our bodies start filtering the excess phosphate through the kidneys. The excess phosphate, having surpassed its renal threshold, cannot be reabsorbed back into the body, so as a result, it remains in the tubular fluid until it can be excreted. Once excreted, phosphate buffers urine as it forms simply by removing hydrogen ions secreted into the tubular fluid. None of the other body buffer systems that we originally talked about is present in the tubular fluid to buffer urine during its formation, so phosphates are very important urinary buffers. Almost all of the filtered bicarbonate and carbon dioxide are reabsorbed, whereas hemoglobin and plasma proteins are not really filtered. Those are the main chemical buffer systems discussed in our textbook. I have included the second to last slide to basically give a summary of some of the things that I have discussed in today's video. All of the chemical buffer systems are able to act within seconds to minimize any changes observed in pH. These buffer systems are the body's first line of defense against changes in hydrogen concentration, given that they are the first and the fastest mechanisms to respond. When hydrogen concentration is altered, the buffer systems shift their reversible chemical reactions once to make up for the change. Going back one more time, I talked about 4 different chemical buffer systems. They were carbonic acid bicarbonate buffer system, protein buffer system, hemoglobin, and phosphate buffer system. Carbonic acid bicarbonate and phosphate buffer systems both involve components in reversible reactions. The hemoglobin buffer system basically involves the use of hemoglobin as a buffer, and the phosphate buffer system works just the same, but with phosphates instead. That concludes my presentation for today. I hope this video presentation helped provide an enhanced understanding of the different chemical buffer systems and how they work to adjust pH changes in the human body. Before I end today's video, I want to personally say thanks to my instructor, Dr. B, for an amazing 8 weeks. I have learned a lot and am hoping to retain all of this knowledge for future use. Thank you for always providing helpful feedback. God bless.